Hello, this is Gustavo Oliveira, and this presentation is about an introduction to physics programming. Particularly in this screencast, I will demonstrate how to write a simple soft body simulation using a cloth as an example. Indeed, there will be two cloth demos I will be discussing here. One more elaborate with better rendering techniques, and a simpler one that just focuses on the physics. Yet they are virtually the same as far as the physics programming goes. Once you understand the basic demo algorithm, the more complex one is just an extension. Before we dive into the theory and the code, let's quickly take a look at the final demo. Here's our cloth demo, and it's modeled with this kid's pattern as the fabric. And also there is a marble ball that interacts with the cloth. So I can move the ball in this very slippery surface, and it will collide realistically with the cloth. Likewise, I can move the cloth and then it collides with the sphere, with the marble ball in this case. And here we have in this scene, we have three light sources, one spotlight, which is represented by this moving cone, and it only illuminates what's underneath this cone. And we also have a point light represented by this sphere, which illuminates all the surface that reflects the light of this point light. And finally we have an overall directional light being animated, and you can see by these walls getting darker and lighter. And as you can see also, the demo is totally interactive. So there is, in other words, there is no pre-baked animation, so everything here is physically calculated, so and mathematically modeled with physics programming. So, and this is the demo, and we'll be discussing all the details how you can write this. The prerequisites for this presentation is that you need to have a solid knowledge of any programming language such as C, C++, Java, C#, etc. Here I will be using CX, which is a variant of C++ for Windows App Stores and Windows Phone. However, the concepts here are not limited to CX by any means, neither Windows. You should be able to port this code to the language and graphics API OS of your choice. But you also, to follow these slides, you need to have some knowledge of computer graphics programming. In other words, I will not cover basics of renders such as perspective projections, polygon drawing, coordinate systems, vectors, matrix, linear algebra, and so on. I will assume you are familiar with these concepts. Now let me show you what you're going to be learning here. So although this presentation I'll focus on this cloth simulation that I showed here, so that's going to be the main focus of the presentation. Indeed, we will be building is like a highly simplified version of a physics engine. Therefore, the learning outcomes not only will be this cloth, but you will include understanding of what is an integrator, what are the constraint solvers. We'll talk about collision detection and collision response, and how physics engine interact with the graphics render in general. The motivation for this screencast was a paper I have read a while ago and was written by Thomas Jakobsen. I'm not totally sure if I'm pronouncing his name correctly, but the paper dated from 2001. It's a little bit old, but quite brilliant to say the least, so that to this day I still see many references to his original paper, even in really recent articles of SIGGRAPH and other graphics publications. Unfortunately, the publication is not hosted on this URL anymore, so Thomas moved this somewhere else. But if you search around, you will find in many places on the web. And likewise, the other motivation for me is to get you started with physics-based animation, which is a fascinating area of computer science. First, let's take a quick look at how a physics engine works. In most cases, a physics engine works together with the graphics engine to allow visualization of the results. So the physics engine feeds information to the renderer to move objects realistically, and then the renderer sends the final primitives to the GPU to be drawn. Also, physics engines are clients of usual collision detection system. Some engines, the collision detector is part of some don't. This is because the collision detection is a huge subject in itself, covering many different algorithms. But in a nutshell, the physics engine asks the collision detector if things collided. And then the collision detector will say yes or no. But it's the job of the physics engine to generate the proper collision response. For example, let's say the engine asks the collision system if a particle collided with a sphere, and let's say the collision detector says yes, it did. Now the engine has to decide where that particle should go. Finally, there are two main types of physics engines. One is called mass aggregate engine, and the other one is a full rigid body engine. Mass aggregate engines are simpler, and what they do is try to model objects as a set of particles constrained to each other. So if one particle moves, it affects the connected particles. And this is what we'll be building here to simulate a cloth. On the other hand, the rigid body engine treats objects as a whole, and they are far more complicated to build. And this is because you need to take in consideration the object rotations, which is in mass aggregate engines, we really don't care about the rotations because they arise naturally from the particle movement. Let's take a closer look at how we're going to simulate a cloth. A cloth can be modeled as a grid of particles constrained to each other in a grid-like configuration, as I show here in this picture. In our case, we will be rendering the cloth with lines. So we need to feed the graphic API with points, ending points for each line. So as shown here, here's a small version of our cloth using a set of 4x4 points. And let's say if the dimension is 4, and I mean by that is there are 4x4 in this grid, and let's say the length of the cloth, and then I'm calling length this distance here, and I'll make the cloth square, and we have a grid of 4x4 points, 16 points indexed from 0 to 15. So each cell size then it will be 12, in this case here, divided by 4 minus 1, it's 4 units, the cell size, that's what I'm calling here. And this is because, between 2 points you have 1 line. So if we have 4 points here, we're going to have 3 lines, and for the horizontal and likewise for the vertical. So we can easily expand this to any dimension. Let's say the dimension is d and the length is L. We have a grid of d square points, and the cell size in this case will be L divided by d minus 1. In the next session, I will be actually coding the render of this grid. Basically, I will be converting like a cube sample into a grid of lines in a sphere because I want to eventually the cloth to collide the sphere. I will be using DirectX, but like I said before, you can do this with any graphics API or any graphics engine that you want. You may even be able to do this throughout scripting with 3D modeling package or even a plugin. It's really up to you. I'm here more into the theory than actually the technique. The one important detail is because I'll be morphing this object, this grid, each frame, you must have access to GPU memory so you can change the vertex position directly. There are no transforms per se. I'm not going to apply transformations to these points. If you don't use DirectX, you can skip the next session entirely because it will be very Windows DX specific. But I do always encourage you to stick around because when I start to code the physics, I'll be building the simulation on top of this sample, so it will be much easier for you to follow the rest of the presentation. Let's start the coding part now. But one last word before I get started is that in many screencasts on web you see the presenter is coding everything from the scratch. As you may have guessed, with physics programming, this is not really doable. Unless you want only to print after results to the screen, which would be really hard to visualize, and that's not what we're going to go after here. To show a full 3D simulation, you need a 3D render, and referring back to my slides. But there is really no time to write 3D render. It's too much work. So instead, what I'm going to do, I'm going to modify a preloaded 3D sample that fits our needs. And in many cases, things I'm going to do are not the best coding practice, but we are here after clarity and not clean code. So clarity should be the priority. So I have Visual Studio 2015, and I will create a new project. I'm going to call soft body. Oops. And here, if you put under this templates, under Windows 8 and universal apps, you have this cube sample. Let me just create the project. And it has all the template code I need for this demo. But what we're after, these two files, where the rendering occurs. So I don't really need to worry about this right now. Let me close that. And I'll do a quick compilation. And then I just wanted to show you, the sample runs here. I'll just bring it. It's just a cube, a spinning cube. That's basically what it is. So whatever API you use, there's always like a sample code with a spinning cube, a spinning triangle, whatever. Okay, one thing I'm going to have to diverge a little bit here. So we have an update function, a render function, and these create functions. DirectX, I'm going to need all of these objects because the programmable render pipeline. But there's one thing here that it's a little bit on our way, and that's Windows specific, but I want to get rid of this. So inside of this create device dependent resource, when it loads the picture shade, it creates all the buffers for the vertex, the index. It's using a lambda function in asynchronous reads. And this is because this is a Windows app, phone app, things has to be really fluid. I don't really need this. This gets on my way. It just gets things more complicated than actually helping. So I'm going to get rid of this and just make the loading to be blocking. So just again, for sake of clarity, if you want to look at this code later. But these are basically nameless function pointers, and he uses flags and these tasks just to synchronize the reading. Again, this is too complicated. Let's get rid of this. First, I'm going to mark it off where these blocks are. So sometimes it's a little hard to find. Let me get rid of all of this. I'm going after a completely synchronous reading here. Another block. And that's where it was loading the pixel shader. Actually, let me put a comment here. This is what I'm gonna do this, and I think there's another one that after both shaders are together, and then it creates another lambda function. So I do not need this either. And finally, since it will be synchronous, I don't need this, but I do want to look for this flag right now. I'll probably find it here. See, before it won't render before the loading is completed, but since I'm getting rid of this, I don't need this anymore. Okay, and I have worked offline a piece of code that does the synchronous reading. And let me just paste in here right before. That's doing it. And the only thing I forgot this. There's one namespace in here that I need to add. I went really fast, but I need this namespace. go back to it. And obviously it's returning the binary that I read from the resources. It's into this STL vector, and I need the, I'll just explain what I'm doing here. I'm going a little bit quick because this is not really part, I'm diverging ever from the point in here. Okay, now I have my synchronous reading here. So basically I'm gonna read these pixel shades directly, blocking, and that's the same thing that's doing, but we don't have to wait. The only thing, as it loads, it will call the dispatch of this process events, which keep processing all the background events, so the application doesn't stop completely. So now I see here, so it's just now a matter of, oops, where is my synchronous reading? I will just copy and paste this code in here. So it makes it a little easier. No, that's not what I want. Copy and paste the wrong code. Okay, there you go. So, and then that's the Vertex shader. And the pixel shader, and I mark it off where I was loading. There you go, here. So I believe now this should run. Let me compile, and now it's all blocking. Yeah, it is now. I have my cube, but I got rid of all that Windows specific stuff. It's all these lambda functions. It's a feature of the C++ 11. So it just makes it a little easier for you to follow. Now let's continue with our render modifications. So one thing I did here before I start, remember all these DirectX objects that we need. I renamed them all to cloth. So I just add a suffix to it to make things more clear, because in reality I'm going to add a second object later, a sphere, so we can add collision. So let's just do this way so it makes it a little clearer. Object could put this in an array, whatever, but again, I'll probably repeat myself many times. It's all in sake of clarity. And also here, if you look at this, the original code, it's hard code the vertex positions right here into this array. So I'm gonna modify this, and I'll keep it around so that you see. And then I created, see now it's asking for the pointer for these, the arrays and the size. So anyway, so I will create this dynamically. So I added this. I convert this to a pointer, and then I add the size for this array and the index count. It's just basically a renaming thing, nothing really that difficult. So now referring back to the pictures of the slide, see if I can get it here. So when we were talking about this, so basically we're gonna render a set of lines, constraints, between two particles. So we need to draw this grid, and that's basically a four-dimensional loop. So I'm gonna morph these vertices into something like this, to a for loop, and taking account these considerations here, the size and the length. And let's see, so I have a little bit of code in here that I will paste so that we go a little faster, because there's a lot to cover, so I cannot be typing everything as opposed to other screencasts. So here I will define the particle dimension. For now, let's define as 4. So in the length here, let's not confuse it. Let me put this as 6. So in the size, and now I'm allocating, see, instead of hard coding this, I'm allocating this array, and then I will loop back to the picture. Where's the picture? Here. So I'll just do a two-dimensional array here, and then I will loop through both dimensions. And that's basically what it's doing. It's going from 0 to the dimensions, and then it's creating all these vertices. And here what I did, I subtract the length divided by 2 so I can centralize the class. So let's say when x is 0, and it would be helpful to have the picture. When x is 0, it's 0, 0 point minus the length 2, so 6 divided by 2, 3, so this minus 3. So it basically centralizes this whole thing on the x, z coordinates as 0, 0. And now we need to fix this because this was pointing to the old array, and I will now make this point to the correct array. In the description also I have to fix the size which I calculated here. So I'm going to fix the size. And now I'm going to get a little bit into the X specifics. And one thing about, and then I don't know how you're going to do this with your own engine, and you have to have access to these vertices like I previously said. So the way in DirectX, the way you do this, and let me see if I can just show you here. The description, I will again. When you create these buffers, right, in DirectX, so it's telling this is going to be immutable by default, so you don't have access. But we need to have access because we are morphing this. So what I need to do is basically I need to change few flags inside this default configuration. So basically what I'm going to do here is this keyword, define here, which dynamic means these things will move each frame and the CPU will have access to it. In other words, at each frame, since we are animating all these points, the CPU will have access to these vertices, and they are dynamic. They're not static anymore. This is very important. You need to add these flags. Otherwise, if you're using DirectX, you won't be able to access. And we get to this in a minute. Now let's fix the indexes. The indexes are a little easier because we don't have to change the CPU access to the buffers, so they don't have to be dynamic. So once these index buffers are into the GPU memory, they never have to be touched, so we won't be fixing these flags and because they don't need to be morphed. We're only morphing the positions. So we only have to really fix the index themselves. So I will just comment this code out, including this, and let's work on the index count first because it usually it's easy to get this wrong. So let's see exactly how many index we have to draw the class, and I'll keep referring back to the picture. So if you look at this picture, each line obviously needs 2 points, and so between 4 points you're going to have 3 lines. So if there are 3 lines, right, so and then we will have to do 2 times the dimension minus 1, because let's say if the dimension is 4, I have 3 lines, but I have 2 points per line. So the first thing we will have is a particle dim minus 1, so 3 lines using the 4 as a reference, times 2 because I need 2 indexes. However, this is just 1 row, but then I have to multiply by 4 by the dimension again because I need to draw all these horizontal lines. So I will then multiply this by the particle dim oops, typing here. And that will give a full set of horizontal lines. However, I'm going to repeat the whole thing for the vertical line, so I have to multiply by 2 again. And that gives me the total number of indexes for all the lines, the horizontal and the vertical lines. And now I will just quickly copy and paste a piece of code in here. And again, I have to do this because I'm in demo mode here. I cannot be writing everything from the scratch. And then it's very simple. Now we have the size, the amount of indexes. I'll just allocate the buffer with this index count. And I have to have the size for the entire buffer because that's how DirectX works. I have to pass that when I create the index buffers. And basically now we just do a two-dimensional loop that will go for the horizontal lines. The index will be 0 to 1, and the next parallel index 1 to 2, and the next part 2 to 3. And I'll keep going doing this, and I skip the whole thing to get the horizontal lines. So, and if you see here, for the x dimension, 3 lines. In the case of the dimension is 4 per dimension, 4 points, 3 lines. So the first index, if x is 0, this becomes 0. The next one will be 1, and so forth. And then it loops to the z dimension. So I'm a little lazy here. You can definitely do this, oops, with one loop, but let's repeat the whole thing for the vertical lines. In that basic, I just need to flip x's and z's with one small fixing here, because now I have to skip, so the vertical lines skip a full dimension. So 0 goes to 4, and then the next line is 4, 8, and the next line index 8 to index 12. So in this case, I will keep the same x, but this has to be zz plus 1. And now that we have that, I just need to fix the pointers. So I allocated here my array. And then to the buffer description, then DirectX, you need to pass the entire size of the buffer, which I calculated here as this cloth index size. And then it should be it. Let's quickly compile. Now I need to, because it was drawing as a triangle list. So I'm going to draw this now as a point list, because I'm drawing, sorry, line list, because I'm drawing lines. And finally, yeah, the eye is very close to the camera because this patch is right on the Y0. So let me add, I don't know, make the eye a little distant. DirectX, it was a left coordinate system, but this sample, they set up the matrix as a right hand coordinate system. That means the Z goes away from the camera. Let's quickly compile. And then let's see, I should be able to see it. There you go. I have my little patch. So I converted basically the cube to this patch, which is our grid, which will be morphing into a cloth very soon. And now just to confirm that everything is good, let me go back where I define the dimension. Where did I find this? Yeah. Let's see, let's do a patch of 32. So it might be a much better patch for a cloth simulation. There you go. So this is it. Now I morphed the cube into
a grid of lines, and that's exactly what we need.
Continuing, there's one less important part when we are doing the soft body objects, and it's because we need to morph that cloth. So I'm going to start here from this update function. I will create just a wrapper, and I'm going to call it update cloth, because the way we need to test it if we can morph this vertex correctly. So, and this basically is a wrapper function, and I'll put it right here. And from the update function, I will call update cloth and pass the timer. Okay, and here's where the action is going to happen, because we are going to be morphing these points. So I work it out, another piece of code in here. Let me paste it and explain what's happening. And that's also DirectX very specific. So now we have the buffer where the points are, but every frame we're going to be updating this. So then the way it works through DirectX, you have to use the map call, and then here, when I call map, now the CPU have access, and I can copy points back to the GPU. And this flag here is very important, because what write discard means is that the moment these calls happen, everything there is invalid. So you need to copy back the buffer. Otherwise, you won't see garbage. It becomes garbage. And this right now is not doing much, because I'm just copying it back. What map is doing here, I get the pointer for the verses. That's basically what map does, and it discards. And this memory copy, remember our P cloth verses where the points are, I copy back exact where the memory is, and we call Unmap. Now the GPU can just use this buffer. At this point, let's just build the code. Nothing different from the previous one, but there's now a significant difference, is that visually nothing changed, but I am actually updating all these points every frame, and that's very important. And just to confirm that this is working, let's quickly hack something here just to test it. I think this one. Let me move this to the header file somewhere. Just outline this a little bit so I can see things more clearly. And let's go back to our map function. Before I copy, now I'm going to try to do, I'm just simply going to try to update one row of points just to make sure this is working. And so where's our pointer? Oh, wait. Right here. And now I will just do a simple thing here. I will just make each y coordinate of one over row of points that keeps going up every frame, and that way we can confirm things are working properly. So I can modify these points any way I want, and there we go, and it's exactly what I want. So there is, I have full control of the vertex position now. The CPU is writing to it, and that's what is necessary for the simulation.
Let's continue with our final modification of the render for our class simulation. So what I did here, I just replicate all these objects, because I'm going to draw now a sphere. And the reason, because we're going to collide the class of the sphere to show collision detection, collision resolution. So anyway, so I just copy and paste these objects and I rename them and I call them a sphere. You obviously can do something better, but you know, let's keep going on our demo mode. And here what I'm gonna do, I'm just gonna wrap this. I'm gonna create a render cloth and a render sphere. And for the create functions, I will also wrap it. I will create a create cloth and a create sphere. And then let's continue here. We're adding our wrappers. Create sphere now. And now so this is our cloth. I will get all this code and that becomes our official cloth creation. And here I'll create cloth. Create sphere. And now the sphere I will just, it's not loading. This is, let me get rid of this. It was loading directly. So I will then paste this in here. And now it's just a matter of renaming things around. Oops. So I will rename here. Cloth just here. And now we have these two objects. And same thing for the render. Let me go back here. Let me make cloth. Render sphere. This is rendering the cloth. Now I'll render this one sphere. I also have to rename everything. Oops. And for the sphere, we can go back and draw as a triangle. Doesn't need to be a wireframe. It will be easier to visualize. Render cloth. Render sphere. Just quickly compile. Should compile. Okay, now if you remember here on our when So we had to modify to create the plane procedurally. So you can do the same thing for the sphere. But instead of doing this, I'm going to cheat a little bit, because we can then draw different objects later if you decide to try to explore different types of collision. So I'm going to bring in my friend the Blender, and what I'm going to do, I'm just going to create a UV sphere. I don't really need that many segments, and I'm going to make, so this is the diameter. I'm gonna make a one unit sphere, size of unit. And then here in Blender, oops, so it's selected. If you go add modifier, remember we are drawing everything as triangles. Zoom in a little bit. I'll put a wireframe. Now I have all this here, all as triangles, and I'm going to go in export. And there are different file formats here. Some are text, some are binary. So Collide is a text file, but I found it really fat. There's a lot of stuff in there. This one I like, the X3D extension, which is pretty clean. So I will export this, and then so I'm bringing here Notepad++, so just quickly show you. So here's our sphere, and then you have here the index list -1, because this was a quad and then I convert to sphere, so we just skip this over, and those are the points of the sphere. So then you can basically parse this any way you want. You can even, if you want to write a little macro like this, you can keyboard macro, and then you can create the list. The only thing you need to be aware is, like, when you look at Blender, the z-axis, see if I can, anyway, the z-axis and the y-axis are flipped from our coordinate system here, and there's no way to change this in Blender, so you need to flip the y and z. And so what I ended up doing, I just wrote a little Python script that parsed that document, and it spits out the text file. And you know, it's very simple Python. I'm not gonna go into this. And so at the end, I have my indexes here in my vertex format the way you want, the way I want. So now back to our code. Oops, let me just. So I'm gonna go in here first. Let me fix the vertices here. So I already worked it out, a piece of code. I mean, it's pretty much the same thing, but let me just get rid of this whole thing with generating the plane procedurally. Yeah, now I just, the text file I generate, I just include into this array. And for the index, the same thing. Let me just paste my modifications, almost back to the way it was originally. And there we go. Let's see if it compiles. There was one small error in here. Let me work out this problem. Let me pause for a second. Oh, never mind. Because it was a bad copy and paste, so I actually did the same thing for the Vertex. So this code is repeated in here, so I don't need this anymore. And I fixed. In the Vertex, I did the same thing, and now I think it's good to go. It was just a copy and paste problem. Let me compile this, and now we should be able to see. There you go. I have my little sphere there with my morphable object, and that's the basic elements of the scene. We can then move on to finally start coding the physics. One extra thing. Let me pause it here. Yeah, and I just noticed when I create I did this on purpose. I actually put the plane on the Z, the Y as 2 units because I wanted the cloth to fall in the sphere. Just to show it because it was a little bit hard to visualize. I'm putting at the Z, at the Y at Z 0, and I can zoom in a little bit with the camera, and so we have a better view of the 2 objects. And there you go. But I will bring this back because I want the cloth to fall in the sphere. And that finishes the basic part for the rendering, the objects, the scene we need to start animating this with physics simulation.